Experimental control consists of two parts. First, we need to identify the background factors relevant for a particular phenomenon. Second, once we know what these factors are, then we have to look at how we are performing the actual control, how we can influence the system so that we get the relevant background conditions in place. And here we have a number of different strategies. The first strategy is to use a divide between control and treatment group. So we're taking a sufficiently large sample on which we want to perform the experiment, and we're dividing that sample into two or more groups, and we're performing the intervention only on one group, while the other group we don't perform the intervention on. Now, this sounds pretty easy. It often isn't. In medicine, for example, we know that there are large placebo effects. So if someone gets a pill, irrespective of whether that has an active ingredient in it or not, that might already make them feel better. So therefore, you need to sort of make sure that it's only the difference, the only difference is the active ingredient. Hence, the control group also gets a pill, just without the active ingredient in it. So that's a way how to correctly divide control and treatment group here. So we do that in order to have a comparison to the individuals or objects intervened on. And we also do that and ensure that that is the only difference, that the intervention is the only difference between these two groups. And now you can, I think, see why it's important to use the control treatment group division instead of, for example, doing a before-after. Because when you do a before-after, you say, okay, so we want to see whether the lighting at KTH, when we change that, is going to affect student outcomes. And then we compare last year's results with this year's results after we've changed all the lighting in all the rooms. Then, of course, you can see that there are plenty of potential factors that might have changed between last year and this year. So while if we're sort of dividing the student body into two and we're only giving half the new light treatment and the other half doesn't get the light treatment at the same time, then we have excluded a number of potential influences there, and therefore our conclusions can be considered to be more internally valid than in a before-after study. Once we divided the group into control and treatment group, then of course we need to make sure that the background factors in those two groups are the same. So we can do that by either taking the existing factors, like in the field experiment, and making sure that there's nothing that is different in the treatment group than the control group, or we might generate them in the laboratory. In some cases, we might not even need to hold factors constant because we're able to eliminate some of the background factors. So, for example, when we're interested in the falling behavior of bodies, air resistance is one of these background factors. We can, of course, perform falling experiments by keeping air resistance constant, but it might be better if we removed air resistance altogether. That's why people, for a lot of money, build these things, like falling towers. This one standing in Germany, where you generate a vacuum in this tower and then perform falling experiments where this factor of air resistance is removed altogether. And one can do that in a number of cases. We can do that with radio waves in a Faraday cage, or we might try to eliminate gravity by moving far enough from any gravity sink. A special case of elimination is blinding. This is something that affects experiments a lot, both in terms of experiments with humans, where the subjects themselves know what kind of treatment they're getting. That affects them. I already mentioned placebo effects. So I know that I'm getting a treatment, or I believe that I'm getting a treatment. That might have an effect on how well I feel already. And I therefore want to make sure, therefore it's important that we ensure that the subjects involved in the experiments don't know whether they're getting a treatment or not. That's what we, in those cases where we can, where we perform human experiments, at least that's what we call single blinding. We're leaving the subjects in the dark about whether they get a treatment or not.
But then we also have the effect from the experimenter side. The experimenter might read the instruments differently, even without wanting to deceive, when they know that this particular instance is one where from the treatment group. So they might say, I'm really expecting a big difference from the treatment. So therefore, I see that I'm looking at it perhaps in slightly different ways than before. Therefore, you want to also blind the experimenter, and even maybe the person who is analyzing the data, from knowing which individuals were in the treatment group and which ones were in the control group. In those cases where we do perform experiments with human subjects or also animal subjects, we therefore call that single blinding, double blinding. Double blinding is when we blind both experimental subjects and experimenters. Obviously, in the natural sciences, you can't do that. There are no experimental subjects. So therefore, we often talk simply about blinding, meaning we're blinding. We're leaving the experimenter in the dark about which objects got the treatment and which did not. Okay, a further form of controlling or performing control is separation. We cannot always eliminate the influence of a factor, but often we're enough to separate out a number of factors. This was the case with the gravity probe A experiment that I told you earlier about. There we had the problem of a Doppler shift in the treatment group. And we didn't want that. The only effect we wanted to have was the distance to the gravity field. That was the experimental intervention. However, with that experimental intervention came that we had to rapidly move the clocks vertically away from Earth. And that inevitably created a Doppler shift. So we couldn't eliminate that. So what we could do, what the experimenters could do, was to separately measure the Doppler effect. So that we could then have a measurement of the time dilation and a measurement of the Doppler effect. And then we could calculate out the Doppler effect from the signals that we received about the time measurement. And that allowed us to separate out these two factors and only get, as a result, time dilation. So here's a list of 4 potential types of strategies how to perform control.